Last time I tried to do it in a way that didn't really work out apparently. So this time I think I'm going to do a different format where I'm going to show you my ch the chapter pages I've made just recently. I'm thinking of doing more of these, but I was going to do the whole table, but then realized it's really repetitive and it takes a while to do them. I'm eventually going to do all of them, but I guess this is part one of Fourier series and the Laplace transformations. And why am I doing this way is because in this way I can write each step, and what I'm going to do is first I'm going to show you everything, and then secondary I'm just going to move this direction and write everything down again by my own handwriting, so you can now slowly understand it, unlike last time where it was all rushed. So I can just write it down slowly on how the solution is processed and everything. So the first thing we're going to say is the Fourier's transformation. So if you want to just look at what I did, I typed it all out so you can look at that. But here we're going to do the rec function first. The rec function. Basically, the rec function is how do you describe it? It is just a square or a rectangle. Basically, in the time domain, imagine an impulse bulb like this, and then this is negative t divided by 2, and this is t divided by 2. And I have it typed up, so if you want to look at a little more clear, you can just look at this. Look at that. But that's 1. That's our space over here. Yeah. Anyways, yeah, I got some talk that I need to be more clear. So I think just handwriting it is more clear because you follow my instructions on how I'm doing it. So the original definition of Fourier transformation is so-called this. So it is basically infinity to negative infinity of whatever function, which in the time domain, this is the time domain. I should probably write time. And then this will be f of t is how I would call it. And then it would be e to the I omega t dt. So this dt will get rid of all the t's, the time dependence. And this omega over here is our variable that we're transforming to. So if you want to know that this will equal to f omega, basically, uh, sometimes you call it I omega, but omega is the correct variable that we're using. I omega will actually create the Laplace transformation. But in a weird way, we'll see later. Anyways, from this, you have to realize that in this over here, we have 1 as our step function, basically going down like this. What that instructs us to say is that the bounds just needs to change and the function over here is 1 for that bound because everywhere else is 0. So we can just say negative t divided by 2 and t divided by 2 over here. And that's what I chose. If you wanted to do just t, it's fine. But t divided by 2 allows us to, what's the right word? Make the final result more clean. If you know that beforehand, great. That means you already did this before. Anyways, we solved the I omega t over here, dt. And then we get finally over here ei omega t divided by negative I omega, and you bracket out that by t divided by 2, and then negative t divided by 2. I hope this is cleaner than what I did previously, because I was told that it wasn't clear enough most of the time when I did it beforehand. So this will equal, in the end of the day, what will equal is very much ei omega t divided by 2. I think it's a negative over here. Minus ei omega t divided by 2 divided by negative I omega. One thing you realize is that this over here, this portion over here, is basically equal to 2 and I think it's I sine parentheses t divided by 2 over here, this top part. So this thing, and then is that, so you just divide it by IW over here, because this over here is negative. I believe this is actually negative also. This comes from Euler's equation, as we said multiple times. This Euler's equation is going to be important, and we're going to use it multiple times. This is where it comes from. We already derived it before, so I'm not really interested in deriving it again, but just note that it comes from there. I'm not deriving that again. That was a pain to derive multiple times. Uh, Anyways, you multiply this by, I think I multiplied this by t divided by 2, and first of all, this cancels out. T divided by 2 divided by t divided by 2. Why I did that was to get it in a form. If you do that, it is basically t sine omega t divided by 2 divided by omega t divided by 2. What happens here is that if you look at this, this is called this is a function that's specific. What that means is that there's a function called sec, like sine or cosine. It's labeled by let me move like this. We talked about this multiple times, but it's always good to refresher. So this is how it simplifies to the sinc function. And what the sinc function is basically sinc of x equals sinc sine of x divided by x. It's just like a function that uses often. So it's kind of like simplified, and it's a lot of times used for electricity and signal processing. Anyways, that's how you get this simplified form that looks clean and beautiful. And let me double check that I got the same thing when I typed it out earlier. I typed this out to yesterday. No, today, earlier. So as you can see, this was original in here, and we get this format over here, and that is our sinc function. Yeah, this this took forever to get because yeah, that took forever. Next is the Eudorado Laplace transformation. So let me just delete all this because there's no point in me keeping all this. I'm only doing it. I only did that to show you guys. I rather you look at the once again the typed version that I made. So yeah. So erase this. Let me erase this. The next question is the unilateral Laplace transformation. Now, you probably realize by now that I'm using interesting word. I say Fourier transformation, Laplace transformation, but I add certain words to it, like this one, and continuous time. The reason I add those things is because there's different types of Fourier transformation. There's a different type of Laplace transformation, and these are the most useful for solving ODEs, the way I'm doing it, which is the Eudorado and the continuous time version. The other ones are used for something else, like image processing and other stuff. It uses the same principle, it's just harder. It's like one day I'll tell y'all. So this one is gonna be a Laplace one. The thing about Laplace is that anything before zero, if it's a unilateral Laplace transformation, it doesn't matter. What does that even mean? Well, like this example here, we use the example ft equal t e negative t plus t. If I remember correctly, that's what we did. And it's interesting situation. If you graph it, it has something in the bottom. But what we're going to do is just ignore the bottom. We're just going to say that never existed in our life. In all honesty, because it's a signal, usually you use it, it doesn't matter. But in all honesty, usually if you solve this side over here, um, give me the pencil over here. If you usually solve this side, because of how good transformations is, this side is also true usually. But there are times that is not when you use the unilateral Laplace transformation, which is why you can't say that. And you can only say it's valid when t is greater than 0 for the unilateral Laplace transformation. And the reason for that is usually the bound. The bound is 0 to infinity. The non-unilateral is negative infinity, but then you can't solve ODEs with that. So that's why we don't really use it at all. I've seen it before. It's just a pain in the ass if you don't get it. I mean, if you don't use the unilateral one. Now, anyways, we're going to solve this again, and hopefully this is much better for everyone. I'm starting to think that this is a much better way to explain everything because at least I'm explaining with my hands and I'm going slower. I think that was what the comment was asking me to do. So I'm doing it. I hope this is satisfactory. I don't know if it's good or not yet. Maybe that guy will tell me what I need to improve next. Anyways, we go over here, we do L of x, and we do infinity to negative infinity. And then we do t plus t e negative t. I don't mind the constructive feedback. I really want them. So if you think I can improve somehow, please tell me. So I'm just writing it out anyways. So this portion over here is f of t over here, as I said. Anyways, we're gonna split it into two because this is an integral, so you can actually just split it into two. It is not that hard if you split the two because it then turns into basically two integration by parts. Now, I first thought I could do imaginary with this, then quickly realized that it's impossible to do imaginary with. Yeah, I thought I could do imaginary with this. Again, if you want a cleaner look, you look at my typed version, it's much cleaner. And look at my textbook that I just give out anyways online because it's just free if you just look at the link. Anyways, we start with this version over here, which you'll realize sooner or later that, let me erase this thing over here, that we do u equal t, and that's the derivative of that is u du equal dt. And then over here is dv equal e negative s t, I believe, and dt. And you take an integral of this portion, which is v equal, and the integration by parts is one of the most fundamental, easiest way to universally used one after dot product. The dot product is number one always. As said by multiple of my professors that teach dot dot products and integration part, they just keep on saying, "Oh yeah, it's so useful," and it is useful, so I can't really doubt them. This one is this. Again, look at my type version if you want to. If you don't like my handwriting after I'm done explaining everything, it's definitely cleaner and definitely more visible. Anyways, and what did you expect? It's my handwriting. I'm trying to do the best I can with my handwriting, but I know my handwriting sucks. So over there you have the two things, and my S's look like T's, and oh my god. Anyways, you get this thing and this thing, and you get uv minus integral. I believe it was this again, v, and then du. How I know this is just look at the. Let me change color. How do you change the color here? Look at the what's given, okay? And what's not given is in the second portion over here. That's how I memorized it. And and this one's pretty easy. That's the ones that are like, defined. It doesn't have to do any integral. So yeah, so look at the version that is not given, and that's all going to be the second portion of the whole thing. That's how I memorized this for such a long time. That's how I remember it. That's how I use it. And then, yeah, let me erase. Oh, God. How do I erase again? Yeah, I'm not used to doing this whiteboard stuff. Anyway, this allows us to get, let me just write this out. T e negative s t negative s, and I'm just this is the bounds as usual. You can put the bounds later on if you want. It doesn't matter. It should not matter, but I don't know if you care, but sometimes I do care. It just looks annoying sometimes, and I do want to change it sometimes. Anyways, again, you do it with the other one. Yeah, hopefully it's cleaner. Uh, Zero infinity. Yeah, I hope this is better for learning. Zero to infinity. And this one is e to the negative x plus 1 t negative x minus 1 dt. Okay, we have both of them. Okay, so one thing you need to realize is that as e to the negative st goes to infinity, what happens is that it goes to 0. As if you look at the graph, just goes to 0 at infinity. So we know that the infinity of this one, infinity of this one, if you take the limit of it, it will go to, this function will go to 0. Now the question is, how about t? Because t is also increasing. So what you have to do, if you want to do the formal way, because you're going to get t um, e negative st divided by negative s to the limit of t goes to infinity over here plus minus t e 0 divided by negative s for this one. So what you're going to do here is take the LHOP of this, because if you realize this, it's going to be t divided by s e t s. And this is why we love, what's the right word? We love exponential equations, because the derivative of that is itself. So we know that if we use LHOP, this is going to be 1, and this is going to be something with e. So we don't have to look anymore and just say that is definitely going to 0 because the t still exists. And then we don't have to look anymore. That's why we love changing our dimensions into for Laplace transformation. And one of the reasons, there's many reasons that we love it, but one of the reasons is that, and it's not arbitrary that we chose it. Okay. Hopefully that makes sense. Maybe we're gonna go on. Hopefully. Um, oh yeah, that tells you that this is gonna be 0 as usual. Let me grab my paper over here. That's 0. Do 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 do. We're left with this, but you see there's negative negative, so you just have to do a plus plus. And then you're left with integral 0 infinity e negative st divided by negative s dt. And then this one is the same thing. So I'm just gonna shortcut. You know what, I should just write it down. Apparently, it's better to learn to go slow. So limit to t to infinity goes to t e negative s plus 1 parentheses t. But as discussed, it's a negative, so this goes to infinity, and this goes to 0, and then we know that from this inverse, and then this is just a t, so we know that this will go to 0 too. And then we're left with this 0. So, wait, did I do this wrong? I think something's wrong here. Yes, I did this wrong. This is supposed to have s minus 1 negative. Sorry about that. Anyways, te negative parentheses s plus 1 t divided by negative s minus 1. And this will go to, let me check this. 0, 0. This is why I didn't care. It's going to go to 0. This whole thing is going to go to 0. Looks like. Yes. Now, this whole thing will also go to 0 because of t. Yeah, that's why we didn't care. I think, is there a typo there? No, I don't know. But no, there isn't. I think I did it correctly. Good. So what's left is the two end integral over here. No, it's the minus. E negative parentheses x plus 1 t negative s minus 1. This integral and this integral. So if you solve these two, because they're solvable, what you'll get is what you get is not what I expect. Why is there another? Okay, there's a mistake in my typing, I think, because that would imply a s square. And I know that t doesn't have a s square. But oh, it might have a square. Okay, I made a typo here. I'm gonna fix it in my textbook, but for now, just note that there's supposed to be a square here. Looks like I did not put it correctly. Okay, yeah, this is supposed to be s square. Okay, I'll fix that real quick soon. Um, Not right now, obviously, but you can see that this integral will give you basically e negative st divided by s squared plus, because there's a negative, negative, uh, plus negative. Okay, I made another mistake there. There's a negative I'm missing. Okay, this should be a plus then. Oh, whatever. Uh, you basically get e negative parentheses x plus 1 over here, and then this is t. This is s uh, minus 1, so this is plus 1, parentheses square, and this should give you, this goes to 0, this goes to 0 because negative to infinity. Oh yeah, I'm right, I'm right. This should be a negative, this should be a negative, this should also be a negative. And what happens is that because there's an infinity minus, there's an extra minus here, there's a plus here, plus here. Okay, there, good. That's where I'm missing. 1 divided by s squared plus 1 divided by parentheses s plus 1 squared. That was a little messy. I apologize for that. And that was because I made a mistake in my typing, which was a square. I was wondering where that square went to. Um, yeah. But as you can see, it works. I just made the typo here, and that confused me over here. That's supposed to be a square. Yeah, I made a mistake. I'll fix it later. Now again, we'll delete all this. Okay, we're good. We move over here to the next one, which is a pretty simple one. The next one is saying basically that if there's a, let me just get my pencil ready. Over here, we're finally doing another Fourier question, which has a bulb here. Now, we never seen this kind of bulb before. And this bulb is an idealized some kind of force system, very fast, like very fast and going down. Usually, it's a Gaussian, actually, but you know, that's why realistically something like this usually it's like a Gaussian, but the Gaussian equation is way harder. So this is a good idealistic. So it's a good idealistic guess before we actually go insane with it. Um, Now I don't really need to write anything because in reality you just have to memorize because there's not really anything to say here. You can prove it bigger by looking at index notation and all that, but in reality, this highlighted portion is all you need to memorize here. What's basically saying is that if you have a Chronicle delta, you see that t over here, you just plug that t into here and you get it because the area here is 1, and you're basically going to only express yourself at this point, which is in this case 0. So in this case, this at that point is the only thing that shows up, that g of t basic g of t here, but it's f of t here. Maybe I should get my notations like good. But no, sorry, g of t is this. That makes sense. Sorry, I'm blanking. Anyway, this is this. G of t is the Kronecker delta. So it's not really it's a Kronecker delta. Anyway, what happens is basically that it's nothing special because of the integral is just 1. There's not much to talk about here. I don't feel like there's something special about this, so I'm just going to move on. Hopefully, I'm not mistaken. There's something special when you do hard like controls, but until then, with the convolutions, it's not very special. Over here, we have a step function. Basically, this step function is at t equals 0. Now, you can see over here that this is similar to the Laplace transformation, and the integral is very similar over here. That's because over here when you change the domain to that. That's because if you think about it, they're very similar. They're the same integral if this happens. So that's what I want to show you over here. If, because this previous part is going to be considered zero, if we have a step function, the integral of Fourier's and Laplace is similar to the point where you could just put s goes to I omega to switch from it, and I omega to s to switch from each other. So basically, if you look at this final version, you can just switch I omega with s to get the Laplace, and you can switch Laplace by just doing I omega. That's basically what it's saying. That's the only part that's important about this, and I should probably explain that in my textbook. I didn't explain it enough, I think, and I have in multiple space enough to say that. So I'm going to actually say that and down there later. Another fix I need to do. Anyway, that's the whole point of that. And I could go through that, but there's no point in going through that integral again because we did the harder version over here. Yeah. Okay, so you're doing the unilateral Laplace transformation over here. This was an interesting one because I decided to do this because it was the only place I could fit this in. Now this looks like a very hard thing. It is. It's NI, and if I go to Desmos, I can't show you Desmos right now because I am in a thing. So I'm going to draw it out. This thing, if you look at the continuous interpolation, kind of looks like this. What's happening is that you're getting all the NI points, like NI, N, Z. So N equal 1, N equal 2, N equal 3, and plotting them. So if this one is N equal 2, N equal 2 looks like over here, and N equal 1 looks like over here. So 1, 2, this is so badly proportioned. 3, and you interpolate it with, I don't know, Simpson 3, just Simpson, what was it called again? Whatever the polynomial you choose, and you interpolate this, you get this function over here that shows you the continuous version of a factorial. And that's kind of what we used here. And that's what this gamma function kind of shows. This integral over here is equivalent to a xi exclamation point. And now I could prove it, but the easiest proof is basically showcase. This is showcasing it because I mean the proof is insane. So I decided just to showcase it. That shows that this is n to 624. So if you didn't know, 1 exclamation point equal 1, and then 2 exclamation point equal 2, 3 exclamation point of factorial equals 6, because a factorial is 1 multiplied by 1 for this one, and this over here is 1 multiplied by 2 for this one, and this is 3 multiplied by 2 multiplied by 1 for this one, and so forth and so forth. So now that you know that, I can go a little bit more intenser now. That's the background knowledge you need to know for me to start this question. Yeah, I finally found a use for it. It's called proving this. I didn't expect it to find a use over here. So I'm just going to move over here and start doing my integral, or just explaining it out loud. Okay, yeah. So doing a Laplace again of some function equal to integral 0 infinity e negative st ft equal L. Just writing it really fast because we did that multiple times. I showed you it multiple times. I think I don't know what I'm saying anymore. So the original idea was f t equals fn. Oh, that looks ugly. Ft equals tn, like to the power. Now, with the definition of a Laplace transformation, you see that integral infinity, which is e negative st Tn equals dt. Now that question looks like a gamma function, but there's one problem. The the exponential function integral, this doesn't exist over here. So how do you change it? It's called u sub, uh, basic u sub. I think everyone knows it. What am I trying to say? Something new. Everyone knows what a u sub is, like at this point in the time. Okay, so I'm just going to write down how I did it. So this is the original u sub because you want this to be one variable. So you arrange it to get t. That way you can get dt equal du divided by s because you just take a derivative of that to get this. Very simple derivative, right? And then you plug all this back into the original equation. Now I did this type, again, look at the type version if you want to look at it clean. It's really messy how I'm showing off over here. So first of all, e negative u makes sense. That's from this over here. Now next is a tn. Now t is given by this, so we can just do u divided by s, and then you think I'd do nothing else, but the derivative dt needs to be changed, which is du divided by s. Now it's just simplification here. You move all the constants, which are these, out. That doesn't do, not constants, but they're not integralized by du basically. So basically that's n plus 1, and you get 0 to infinity u n e negative u du. Now this integral is the same, and this is actually the same as this integral over here. That is given. I don't have the ability to explain that without going to messy detail. So we're gonna just assume it's true by showcase. So we're gonna, yeah, because I can prove that to you, but it's just not worth it. I don't think there's not much learning to that. So basically this equals basically ni Sn plus 1 is basically what I'm saying. And we use n because we use n for our, placement. So it makes sense for you to, if you could use u, but then you need to say u, z, and then n and z. Just saves the space. That's why I did it. It's nothing special. Anyway, we just finished that. I can now delete this. I hope this is much better for your learning. I don't know. Okay. Next over here. All right. This is my next question I made. Basically, we're just going to the table. If you don't know, there's a Laplace table and there's a Fourier table that makes things easier. Just look it up, and you don't have to do the integral stuff. But I just want to show off how you get each and every one of them until I realized some of them are like very hard to get, and I lost interest in doing them. Yeah. So, anyways, we're doing this now. Sorry for the delay. I went off topic there a little bit. So, yeah. F of t equals EAT now, basically is what I'm doing. And then we already know the Laplace, but we should write it down anyways because actually I don't know why, but we should do it just for the sake of completion. 0 infinity EAT E negative ST dt. For sake of completion, I should probably write that. No, I shouldn't. No, this is completion enough. That means I can do integral 0 to infinity e a minus st dt, and we know how to solve this kind of integral, which is 1 divided by a negative s. I believe that is right. And then that is bracketed by e a negative s parentheses t 0 to infinity. Then you have to realize that you have to get the infinity will go to 0. So, oh yeah. You have to assume this one constraint, but that's not really a big problem. S has to, oh my God, S has to be greater than A for it to really make sense, but at the same time, it doesn't matter. You'll see why, because still 1-to-1, So why this has to happen is that let me show you this limit of t to infinity of negative a negative s e a negative st minus 1 divided by a minus s e to the 0. So over here, you want this to go to 0, right? And then that would equal 1, the right answer, 1s minus a because of this negative over here. That only can happen if this portion over here, oh, sorry, this has to be parentheses. This portion over here overpowers the a and makes it just go to 0. Now, why it doesn't, I mean, it does matter, but why it doesn't matter is that in S domain, what happens is most likely something like this. So definitely go to 0, and this is the place where A happens. This is S domain. So this shoots up to infinity, but over here, as you can see, it goes to 0, so that doesn't matter. Yeah, because it's still one-to-one. Did I explain what, I should probably explain what one-to-one means. So imagine this is the time domain, um, and this is our S domain. So what's happening is that we're dragging from time domain, we're plugging into S domain, and then there's also the frequency domain that we're also plugging into here. And then anytime we want, this must be the same as going back over here if you do the inverse of it. And if you go back over here, it must be the same. That's basically what a domain is. And then, you know, yeah, this is something that is a necessary knowledge in my textbook, which is like in the beginning of the textbook, but it's good to refresh your memory a little bit. Um, Now that's why I need to also solve for the inverse version of these integrals later on, just to show that it works. I only do one of them because those are hard. Those are actually like dastardly hard. Way harder than what I did over here. This part over here is hard, but actually manageable by hand. That one's not. I need to find some special question that is. Um, Otherwise, I'm going to be there for hours trying to figure that out. Probably the table is the best bet. One of the table questions is not that hard or something. Anyways, I am going to a tangent that doesn't need to be here, so I'm going to shut my mouth. Just continue here. Cool. So the next one is the sine one. Oh yeah, the one I went to imaginary for. Okay, we'll do this. We'll delete that. Okay. This one also, look at the typed version. It's much cleaner, much more understandable. We're gonna stop at sine because the cosine is basically the same thing. I just didn't show all the steps because it's the same thing. I don't want to do that again. I just showed the intermediate steps. I didn't show the intermediate step for cosine. I only did it for sine. Anyway, again, for completion's sake, I will write all this out. Hopefully this is way better than what I did previously, where I didn't do this. I know it's a little bit rough because it's my first time doing it, and definitely not going to record this again because it's so much work to do this, actually. So I'm not going to record it. Anyways, so we go infinity e negative st basically, and then we do imaginary world, which makes this. Oh, sorry, this is a. The reason I chose A is because we kept on using A, but in reality it's omega because that's the period or something like that. You keep on doing this, you keep on simplifying. And we all know that imaginary is just a number, so it doesn't matter how you treat it, it's just a number. So you can treat it like any other variable, which means I can do a simple integral here that will give me basically this integral is something like E IA divided by ST 2I IA minus S 0 to infinity like this on the first one. And then the second one is also the same thing. You gotta realize this way earlier anyways to get here, so but it's good to review. Always good to review something that I've done multiple times. Because I made that mistake earlier, right? That I was shocked I made because that was such a new mistake. That's something you would do in when you're learning it, and I still that make that mistake. So yeah. Anyway, now we evaluate this, and we already know that, as I said over here, this will go to 0 because of what I discussed earlier. And we go again, minus IA, that stays, and minus lim t infinity, and we know this is going to be here. But we know this is going to be 0 because the same thing. I did like 5 times, so I don't think I need to explain myself more on that one. And then we left with S plus IA. And now you might think that doesn't look like anything like what I showed over here in the end, but it does when you factor everything, you'll see. So over here, 1 divided by 2I, 1 divided by S minus IA, minus 1 divided by plus IA. Well, you multiply both sides, so this is equal 2I, and then you just say, okay, let's just put that on top. Okay, and you know perfect square, S plus IA, parentheses, S minus IA, that equals S squared plus A squared. So the bottom is going to be S squared minus A squared. And we have parentheses minus parentheses, S minus IA. We know this to cancel out because the minus, but minus minus equals a plus here. And then that means it's the 2IA divided by S squared minus A squared by 2I. We know the 2I cancels out, which equals A divided by S squared minus A squared. Ta-da! We're good here. So yes, I get that. So the only mistake I made was this one over here, where this should have been a square over here. But that's it. I think we're good. With that said, I'm gonna stop recording and edit it a little bit. But I hope this is better. I hope showing this off is much better than before.